Hey guys, I've been working hard on preparing a lot of selenium chemistry, and in this video I'll showcase the reactions of elemental selenium and some of its compounds. Additionally, in one of the upcoming videos, I'll demonstrate reactions involving pure selenic acid. I already filmed almost all the material, and I'm aiming to publish this video next month. So let's dive into the world of selenium chemistry. Take a look at these gray pieces lying on my palm. These are pieces of selenium, more precisely, black vitreous selenium. During storage, its appearance has changed slightly. However, if we split this piece with a hammer, you'll clearly see a shine similar to that of broken glass on the fragments. This is what a fresh 1 ounce ingot of vitreous selenium looks like. However, in a lab, the commercial form of this element is more commonly found in the form of granules, resembling erythrocytes. Selenium melts at about 220 degrees, turning into an almost black liquid. Selenium vapors are dark red in color. In the gas phase, selenium exists in the form of diselenium molecules. If we place an ampule with selenium vapor in the electromagnetic field of a Tesla coil, we can observe a blue-violet color of a selenium plasma. The selenium vapor cools and settles on the walls of a test tube. On the hotter part of the tube, we see black selenium, while on the colder part, we see red selenium. This is because slight heating causes red selenium to transform into black selenium. When molten selenium is poured into cold water, you can observe how granules form from the molten drops around the frozen mass of selenium. In slow motion, you can clearly see reddish air bubbles forming around the granules. These bubbles are air around which selenium vapor has condensed, giving them a red color. Look at these beautiful freshly prepared selenium granules that I just took out of the water. I placed them next to a stored sample for a clear comparison. With significant zoom, you can observe inclusions of red selenium within the remelted piece of selenium. While shooting this video, I poured molten selenium into the water multiple times, and in one instance I obtained this peculiar figure. Like plastic sulfur, molten selenium can be drawn into a long thread. Now we will prepare a sample of red selenium by adding dilute hydrazine hydrate to a solution of selenious acid. Upon contact with selenious acid, hydrazine hydrate instantly reduces selenium, resulting in the release of the red selenium and turning the entire flask contents red. Red selenium is similar to fresh red phosphorus, albeit slightly lighter, and in hot water to it instantly transforms it into black selenium. That's why a dilute solution of hydrazine hydrate is used in the reaction with selenious acid. If we were to use a concentrated solution of hydrazine hydrate, the strong heating from the reaction would yield a mixture of red and black selenium. Of course, I tried very hard and prepared the reaction of anhydrous selenious acid with anhydrous hydrazine. Let's see this reaction. In this apparently exothermic reaction, black selenium is mainly formed instead of red selenium due to the high temperature. Red selenium can also be obtained by passing sulfur dioxide through selenious acid. To demonstrate the combustion of selenium, I placed it in a quartz tube and supplied it with an oxygen flow. If we continue heating after the selenium melts, a blue flame will soon appear above it, and the selenium will begin to burn rapidly, forming selenium dioxide. Selenium dioxide exists as white crystals, however, upon ultra-macro zoom, particles of red selenium can always be found. Even dust is capable of reducing red selenium from its dioxide over time. This reaction of selenium dioxide with anhydrous hydrazine proceeds more vigorously than with selenious acid. When heated above 300 degrees Celsius, selenium dioxide sublimes in the form of long white needles, and its vapors are colored green. Now I invite you to observe the reaction of anhydrous hydrazine with selenium dioxide vapor. Pay close attention to the distinct black droplets descending to the bottom of a test tube. Thanks to the slow-motion footage, we can witness the transparent drop of hydrazine becoming coated with black selenium as it reacts with selenium dioxide vapor. Selenium dissolves in concentrated nitric acid to form selenious acid and nitrogen dioxide. When heated in concentrated sulfuric acid, selenium dissolves to form a dark green solution of selenium sulfide. This reaction is reversible, and upon adding water, the equilibrium shifts to the left, resulting in the formation of red selenium. Adding concentrated sulfuric acid helps shift the reaction equilibrium to the right. By dissolving iodine pentoxide in water, we obtain iodic acid. Selenium dissolves in it, forming selenious acid, while free iodine is produced, causing the solution to turn brown. Placing an alkali metal or a few drops of sodium-potassium alloy in molten selenium leads to an explosion. The reaction proceeds similarly with potassium. In these reactions, alkali metal selenides are formed. When a few drops of water are added to them, red selenium is produced. When a mixture of iron and selenium is ignited, iron selenide is formed. Iron selenide does not react with water, but reacts with hydrochloric acid, resulting in the formation of hydrogen selenide. Lead nitrate powder instantly darkens upon contact with hydrogen selenide. Now I'll show you the reaction of selenium and chlorine. I pass a flow of chlorine over selenium in a glass tube. No heating is required as it is a self-heating reaction. During the reaction of selenium with chlorine, a red liquid called diselenium dichloride is formed along with a yellow powder known as selenium tetrachloride. When heated, selenium tetrachloride sublimates instead of melting. Selenium can be dissolved in water by passing a stream of chlorine through it. Based on the previous reaction between selenium and chlorine, it's easy to understand the process of dissolving selenium in water in the presence of chlorine. When a selenium powder comes into contact with chlorine bubbles, the same red liquid from the previous reaction is formed, which then dissolves in water. Take a look at this ampule. It contains pure selenium tetrachloride. This substance is sensitive to moisture in the air, so it's best to store it in sealed ampules. These are pale yellow crystals that fume in air. They are primarily used in organic chemistry to obtain selenium-containing organic compounds. When selenium tetrachloride reacts with hydrogen sulfide, it forms red elemental selenium and yellow elemental sulfur. The reaction with sulfur dioxide proceeds much more slowly, but it still leads to the formation of red selenium. If we add a small amount of selenium tetrachloride to hydrazine hydrate, a vigorous reaction occurs, releasing red vapors of selenium. Due to the substantial heat generated during this reaction, we can observe a resulting black selenium. As with most other selenium compounds, anhydrous hydrazine reacts to form mostly black selenium due to the high reaction temperature. Thanks for watching, guys, and be sure to leave a comment if you enjoyed learning about selenium chemistry. Let me know which other reactions you'd like to see, and stay tuned for an upcoming video on selenic acid. If you enjoy what I do and would like to support me in creating more unique chemistry content, consider becoming my patron, as many of my viewers have already done. I'm immensely grateful to them. Your support is vital in enabling me to explore and create exotic chemistry videos. See you next video.